Dear participants, we shall start the day 1 session 2, and the session speaker is the Dr. Mahadev Prasanna sir, and he is going to deliver a talk on advances in signal processing. So to start with, we have a brief introduction. Let us see the brief introduction about sir. So Dr. S R Prasanna is a dean in faculty welfare research and development, and working as a professor and working in the Department of Electrical Engineering at IIT Dharwad since July 2007 to till date. So he was a faculty member at the Department of Electronics and Electrical Engineering at IIT Guwahati from August 2004 to July 2017. He was also worked as a Dean Research and Development from July 2015 to July 2017 at IIT Guwahati. He obtained his PhD in Computer Science and Engineering from IIT Madras in 2004, and also he has secured his MTech degree in Industrial Electronics from NITK Surathkal in 1997 and BE degree in Electronics Department from SSIT Tumkur in 1994. So, to his credit, he has a voluminous research awareness and contributions. He has guided 20 PhD theses and 10 ongoing theses in the area of speech and handwriting processing. So, he has published over 250 research articles in reputed Indian and international journals and conferences. He has executed large volume funded projects and also provided consultancy to many public sectors and private limited companies in the area of speech processing. Sir, we are happy to have you in our session. So, and we are looking forward to enlighten our knowledge with your speech in this area, sir. So, I hand over the session. Once again, I welcome you, sir.
Okay, thank you very much, madam. Thank you very much for this opportunity.
Thank you.
It's heartening to see there are many FTP programs on speech and language processing. So it will be an honor to present some thoughts in that direction. So when Madam contacted me for this talk, I thought about I will inform the audience about the development that has taken place and continuing to grow in the speech processing area. Of course, without exception, some of you are following the literature, either in speech processing or in any other general area. People are talking about nowadays artificial intelligence, machine learning, and deep learning. So speech processing is not exception to that. In the last one decade, a lot of speech technologies have been developed by using this deep learning approaches. Of course, first area, to the best of knowledge, was image processing, which exploited these early trends in the deep learning. After that, in 2012 onwards, speech processing area started using these deep learning trends. And we are able to see some commercially viable technologies deployed in the field, which was not possible in the earlier scenario, that is before 2010, whatever the technologies were there. So I would like to explain about the trends that took place, which resulted in the speech technologies which are commercially viable nowadays. So there are effects of that also, how it will be beneficial for speech processing in Indian languages also, I'll briefly mention. Of course, at any point of time, if you have any questions or something, please feel free to interrupt me and ask questions. Also, if there is any issue with the sliding, sharing the slides as well as my voice, kindly alert me. I have organized my thought in this direction. I'll briefly introduce this fascinating field of speech processing. Of course, if you want to appreciate the latest trends that are happening in the speech processing area, we need to demystify these four terminologies that are making rounds in terms of artificial intelligence, pattern recognition, machine learning, and deep learning. I will briefly explain about, without taking any particular technology into consideration, how uh, as a first level, maybe generation one of speech processing, how people did speech processing using pattern recognition approaches. Then as a generation two, how people did speech processing using machine learning approaches. And as a generation three, how people are working on developing speech technologies using deep learning. So that is the way I have organized my presentation. Once I reach this deep learning trends, I will take few examples, mainly used speech technologies like speech recognition, speech synthesis, speaker recognition, language identification, how I will compare some of the published results, not from our group, which is publicly available from other groups, to send out a message that how significant the effect of deep learning, that is the latest trend, in improving the performance of the different speech technologies. This is essentially to inform you all that who are interested in the speech processing. Deep learning, without any doubts, is going to be a technology which will be useful for developing robust speech technologies. In that way, there are studies both in speech processing and even natural language processing also, which have beaten the traditional paths and told that with the help of deep learning, we can try to overcome some of the major bottlenecks or difficulties that are present in developing technologies for speech processing. Especially when I take Indian languages, we have a large number of spoken languages. We have 22 scheduled languages plus one English. Apart from that, we have a large number of tribal languages, runs into several hundreds. So the traditional approach of developing speech technologies that we were following in the era of pattern recognition may not, or even machine learning, be an approach. If we want to take that path, it will take several decades to bring technologies for all Indian languages. Alternatively, if we want to tread this path of deep learning, there are approaches where I can automate many processes in the technology development process. Several modules can be automated. Deep learning will take care. And so in that way, there is a fast turnaround time for developing speech technologies. That is one advantage of this latest trends in the speech technology. See, one advantage of this deep learning, the latest trend is we will be able to develop speech technologies for many Indian languages in a fast turnaround time. That is one part. The second part is, see, earlier we were essentially focusing on developing these major speech technologies like speech recognition, speech synthesis. At the most, we used to go for speaker recognition and language identification. Beyond that, we were not bothering much about developing different speech technologies, even though some basic R&D is being done. Now it is the time people are thinking about some higher level tasks in speech processing. So people are talking about modeling the higher level information present in the speech. What is that higher level information? I'll briefly talk about. Because when I take speech, it is a modality for communication, essentially a cognitive process, which has much more information compared to what we exploit only for speech recognition or speaker recognition or language identification. So now people are talking about that. So that is now we can also, if we are interested, we can also tread in that way. Because earlier we used to say we have not yet solved or brought the performance of speech recognition, which is an important technology, to human level performance. Then how do we worry about the other tasks, complex tasks? But now, since now the current trends are showing speech recognition technologies which give human level performance, we have the luxury to think about modeling some other additional information that is available in the speech. That is another trend which we see nowadays. Well, these are some introductory slides. I think some of you, if you have attended some other faculty development programs where I gave talk, maybe some of them you might have, some of these slides may be repetitive, but I will try to add some value to that. See, when I come to the speech processing field, it is quite distinct compared to the communication field, because generally we feel that no, if I have done research in digital communication where I also process voice signal through the digital communication channel, I know what is happening in the speech processing. That is not the case. When I go for speech processing, we are focusing on mainly modeling the information that is present in the speech signal. So what is that information means? The first thing is it is essentially meant for conveying the message part in the spoken form. That is what we decode. Suppose I am talking now and you are all listening. So your cognitive system is through your reception mechanism called ears. Through that, it will receive the speech signal and comprehend the message part that is being conveyed. You can also identify the language in which I am producing the speech signal. That is also another information source that is encoded into the speech signal. Similarly, this is the person. Of course, when we are interacting for the first time, it may take some time to register the speech signal uniqueness with reference to me. But otherwise, if some of you have heard me or known me earlier, even when I speak one phrase, you will be able to say he is that person. That means to say the person-specific characteristics are embedded in the speech signal. Similarly, you will be able to make out whether it is a male gender, female gender, like that. So the gender characteristics are embedded. Similarly, the emotional status of the person, whether it is a happy, angry, sad, or any other emotions. In that way, so there are many higher level information sources that are embedded into this complex speech signal. And our human brain is capable of focusing onto one or more of these and perform the intended task. And nowadays, we have capabilities with the help of deep learning. We may be able to pursue our research and development in modeling one or more of these information. Uh, of course, all of us are the examples for this. As a human cognitive system, we are very good at modeling information that is present in the speech signal. So if I know the language information, I can completely understand the message being conveyed. I can also identify the language in which the message is being conveyed. I can also identify the speaker characteristics and so on. Our human cognitive system is well tuned to extract these different information sources that are present in the speech signal. Another beauty of human cognitive system is it can provide a selective attention. That means to say, if I'm interested only in decoding the message part, the other information sources which are there at the same equal level in the speech signal need not form as an obstructing block for decoding the message part. That means to say, when I'm trying to do message decoding, then I can selectively neglect the other information source like language, speaker, gender, all those things. Okay, that they will not become a problem for decoding the message part. This selective attention is one important aspect of human cognitive system, which is a higher level task, which we have not understood clearly how human cognitive system does that. What we are witnessing is, yes, speech is being processed by our cognitive system and decoding the information. What we have dreamt as electrical and computer engineers or scientists, we want to give this capability to the computing machine to mimic one or more of these activities. Suppose if you consider a automatic speech recognition system or technology, which is available nowadays on computers or embedded device, or even a simple output device like Alexa or some other embedded device, or even cars and other places, which are embedded devices where it just records the speech signal and gives it to the server for decoding, and then based on that information, action will be taken place. We are trying to mimic such activities on a computing machine. So the whole efforts that has taken place, starting from maybe early 1960s in the electrical communication area, we can broadly group all these approaches into three categories. One, those class of methods which are approached by using what is called the pattern recognition area. The other thing can be grouped under what is called the machine learning area. The third one, the latest trend, is in terms of the deep learning. Of course, they are not really isolated verticals the way I am trying to put, but initially it is better to appreciate the differences among these broad areas. Then later we may combine them and try to use interchangeably also. By that I mean, if you see, the pattern recognition can be treated as the earliest trend, then as a later modification of that, this machine learning came. Of course, there are different stories in that way, where pattern recognition is a terminology more came from electrical engineering. Machine learning is a terminology came more from computer science domain. Like that, there are several things. However, we can see the philosophy, what is guiding each of the directions. Based on that, later we can, even if somebody is talking interchangeably, we should not mind. So that is what of course, if you see, when we communicate across humans, we can do by either oral mode of communication or non-oral mode. Oral mode means either you produce speech or you produce non-speech entities via oral cavity, like laughing, crying, coughing, etc. They also convey some information, but there may not be any linguistic meaning for them. Similarly, non-oral means we have written language, which we use extensively. Sign language, who cannot speak, we can use the sign language. Speak or understand spoken mode, we can use sign languages. Apart from that, we can also indicate gestures, body language, etc. These spoken language, written language, sign language, which are backed by some linguistic dictionary, they can be treated as verbal communication, whereas the other things can be treated as non-verbal communication, as shown in this slide. Now, focusing just on the speech communication, you will have just like a communication system, broad block diagram, you need a transmitter, receiver, and a communication channel. You need a talker, listener, and a media connecting them. Suppose if I take the talker, from her cognitive system, she generates the message to be conveyed. She uses, based on the message to be conveyed, the neuromuscular commands are given to the speech production system, which modulate as a function of time, which essentially results in modulating the airflow, which is exhaling out of the speech production system, which results in time-varying acoustic pressure variations, which we call it as speech signal. And this speech signal through the atmosphere reaches the listening part of the listener, which is ear. Through the ear, the acoustic pressure variations will be funneled in, and in the inner ear, the acoustic pressure variations starting from middle ear, acoustic pressure variations in the middle ear get converted into mechanical vibration. From the mechanical vibration, they convert into electrical variations in the inner ear, which are bioechoed potential, put onto the auditory nerve and goes to the brain, shown as E, brain of the listener. And his brain, which is a higher center for learning, it decodes these bioechoed potentials and comprehend the message that is being conveyed. Okay, so this A and E the higher centers of learning, cognitive system, where how a message formulation takes place in the mind of the talker and how it gets coded into a specific language. Even though a lot of studies are going on in the brain research by neuroscientists, not clearly decoded completely without ambiguity. Same way, from the biocode potential, how do you decode the message part, the comprehension part? That is also less understood. So as speech processing practical team of developing speech technologies on a computing machine, since we have not understood A and E properly, we mimic in our own way based on the latest trends available at that point of time. We are trying to mimic that activity, just mimicking the activity, but not exactly the way human cognitive system does it. Because since we have not understood, we can't mimic, we can't put or emulate that. Rather than that, we are mimicking that activity for achieving the goal. By that I mean, all of us do speech recognition, human speech recognition, when we receive the speech signal from a known language. But how do exactly I do speech recognition in my higher centers of learning? It is difficult to put them in an algorithmic fashion. Oh, this is how I am decoding into sequence of basic sounds and then combine them to form a words, although it happens so instantaneously and different mechanism. So that is where, since we have not decoded that well, we only mimic. Yes, we understand. We will try to mimic that on a computing machine. How do I mimic that? Whatever the latest trends are available in the speech, in the electrical engineering and computer engineering, you exploit that and try to do that. Of course, if you see that in the talker mind, the information is available in the linguistic level, means whatever the message I want to convey, first I have to code that in one particular language, spoken language. That is that linguistic level message. From that linguistic level, it goes to physiological level. Physiological level means it will the mechanical motions that will happen in the oral cavity, and that comes to, at that level the message gets translated into physiological level. From there, at the output of the oral cavity, it becomes an acoustic pressure variation. It gets transduced into acoustic level. From the acoustic level, again it gets back into physiological level in the ear. From the ear, it goes to the brain, where it becomes a linguistic level information. You can see it completes the cycle. In the higher centers of learning, it has to be in the linguistic level. Again, in the listener higher center also, it has to be linguistic level. But to accommodate the media in which we are communicating, it gets transduced into different levels and then conveys information to the next level. So, as I told, we want to mimic some of these speech, spoken language processing related activities on a computing machine. People always took this as a challenge in a computer science domain. We want to build computing machines that are more human-like. More human-like means we provide abilities to computing machines which can interact with the external world just like humans interact. How we as humans interact? We interact with the external world through our sensory mechanism, the 5 sensory mechanisms we have. One of the sensory mechanisms, even though I am biased to say that spoken mode, the speech mode is one where we can produce speech and also we can perceive speech. That is one mode of interacting with the external world. When we are telling we are developing computing machines which are more intelligent in terms of interacting with external world like humans, speech also forms one important aspect. Same way the natural language processing also. So we as a speech processing community, we were interested in coming up with computing machines as different generations that can behave like humans in the form of speech modalities. Even though it was a very good goal and people thought in next 1 decade or so we will be able to solve, even though this goal was set in late 1960s or early 1970s, people felt that no, it can be done maybe as a just like our telecommunication standards come 3G, 4G, 5G, we can do it in next 5 years or 10 years. But when initially they attempted, they felt that uh, it we have not understood much about this cognitive process. So hence, it became very hard to mimic that activity, mainly because they appreciated that this is because of the cognitive nature of this spoken mode of communication. That is the reason why they felt it difficult to mimic that or realize that goal. Uh, Day by day, it was proving very hard to get a performance which is equivalent to that of humans. It became an elusive goal starting from 1960s till 2010 or so. Uh, as I mentioned here, till last decade, till 2012 or so, people were developing speech technologies and say that no, we have a much improved speech technology compared to our previous version. None of them were robust enough to be deployed in the field. Okay, so in that way, they remained just as laboratory demonstrations. After this deep learning ventured into the speech processing area, they were able to put speech technologies which are commercially successful. I think if you go back and look at last 1 decade in the speech processing area, the Apple company Siri made a big news. Oh, that works well. Apple Siri works well. People were talking. Then came Amazon's Alexa. Then rest of the things came. Even though if you see earlier, Microsoft also long two decades back, if I'm not wrong, they were bringing with a dictation machine where you don't have to type. You open the dictation pad and speak into it, it will type. But people felt that there are a lot of errors that were happening in the dictation. So as a result of that, they were people quickly felt that no, okay, this cannot be used. They reverted back to typing the message. But now, once this Amazon Alexa, we see advertisements, even Google Home and other things, where we have put these devices for collecting the speech data in the natural environments where there is no restriction. Highly reverberant, highly noisy acoustic environment may be there. Highly noisy means a realistic environment like home, offices, and all those things. There are no restrictions onto that. You have to acoustically treat the room, all those things. And we are able to produce speech. It can recognize collect the speech and process it and do the task what we require. You can recall some of the advertisement given for this Google Home or Amazon Alexa. Even recently, I was having an surprising experience with a private banking. It calls. It's all completely automated. A call center operator, even though to give a feeling that the other side party is a human person talking, it will say some name, Indian name. I'm so and so speaking. Can I have few minutes of yours? But as a curiosity, if you see, he is not a human person. It is an automated speech recognition technology and speech synthesis technology. So it will ask me, suppose if I have not paid some insurance premium or something. So it will ask me, so you had this premium and am I speaking to so and so? It's a dialogue. Then I say yes. Then it's okay. Thank you for so I need your 5 minutes. Can we proceed with the conversation? Then it will say yes. If I say yes, then it will go further, saying that your premium supposed to be paid on this due. Have you paid this? And if you are not paid, how would you like to pay? Whether you go by online, offline, everything is completely automated. On the other hand, if I say no, I cannot continue the discussion, it will ask, okay, thank you, but when should I get back to you? So you can see that it is almost nearing the performance of a human call center operator. Okay, of course, there are some awareness is required, but what it is trying to manage in the Google, Apple series, not Apple series, it is trying to manage in the dialogue way of handling the errors. Okay, that is what is happening. Of course, in a cooperative scenario, nice to get. Otherwise, rather than all of us are frustrated with this call center operations where it will put you into hold for nearly 5 minutes, 10 minutes, saying that no, you are a valued customer, just you suffer for another 15 minutes, then we will see. But now it's no more the case. See, the artificial agents will take over, and no, you give a cooperative this one, you get the information, whatever is required. Okay, so this type of technologies, commercial viable technologies, can be attributed to this latest trend in speech processing, what is called deep learning. Okay, and this story may be true in other areas also, but I am just focusing on the speech processing. Of course, when I say deep learning, we should, of course, these concepts, whatever the models or approaches that we are putting under this framework of deep learning, people explored this in as an advanced topic in neural networks in 3 decades back itself, like convolution neural network, recurrent neural networks, time delay neural network. All these things were there. Conceptually, they were there. But when they trained those models, the performance was not coming in the way what is expected. So that's where it became just a theoretical interest. People left it there. But what happened was the latest computing infrastructure in terms of GPUs, as well as the huge heap of digital data, which is nowadays, it is really, really easy to collect speech data. Because of these two factors that fueled or rekindled the interest in the deep learning area. And it really exploited the potential of the deep learning model. So in that way, the credit goes not only to the deep learning, but also the computer architecture people who have brought this GPU architecture, and also connected world, where you can collect data sitting in your office from any corner of the world. These two infrastructures gave a real push to the deep learning technology. Of course, I told we need to demystify these 4 terminologies like artificial intelligence, pattern recognition, machine learning, deep learning. Now, without exception, any industry you go, company you go, whether it is construction company to high-end IT company, they all talk about artificial intelligence. So we are now next, the thing which is going to happen is AI-based system. If you see when initially artificial intelligence terminology is not new in the computer science domain, it is there as old as pattern recognition. Only if you see in one sentence, if you want to say artificial intelligence, again, it refers to the approaches that enable computers to perform intelligent tasks. Okay, intelligent task means, see, when as humans, we exploit our cognitive system either in a localized or a globalized sense to interact with the external world, whether it speech mode of communication or visual mode of communication, or driving, or any other activity that we do on a daily basis. It needs the effort of cognitive system. And all those tasks that we do with the help of this cognitive system, these are called as intelligent activities. Okay, and this type of doing the activities with the help of this cognitive system, those we are calling it as intelligent activities. And when it comes to the field of artificial intelligence, we wanted to mimic the activities that humans do with the help of this cognitive system. Of course, since it is less understood, we only mimic that cognitive activities, and that is where it is called as artificial intelligence. The activities done by the humans with the help of cognitive system, they are called as intelligent tasks. And when we are trying to mimic these intelligent tasks on a computing machine, these are called as artificial intelligence. Okay. So here, when you go to this field of artificial intelligence, this is one, as a level 1, what people understood was, okay, human cognitive process is a very complex process, and how humans are way above computing machines when it comes to these cognitive activities or intelligent activities. So that we want to enable the computing machines to do that. This field of artificial intelligence was coined, and there are elective courses, all those things. Research. One direction in the artificial intelligence was again observing the human. Then people paid attention more and more. Okay, if we don't deeply understand how the cognitive process takes place, at least can we? It is like a black box testing like thing. Can we try to decode some phenomenon of this intelligent activity of how humans deal with the external world? That is where they came up that comparing with the computing machines, humans treat when we are interacting with the external world, better deal with external world as a cognitive activity, we use what is called a concept of pattern. Uh, See, if you can, I can give any number of examples and you can appreciate that. In our daily life, we remember something, or we deal with some situation, or we are able to move on or cross over to certain hurdles, mainly because of uh, some knowledge that we have in our cognitive system, which is stored in our cognitive system because of our earlier experience. Okay. And we are trying to look for some such behavior, which we call it as a pattern. Okay. We don't look for data, whereas computers look for data, whereas as humans, we look for patterns. Patterns mean, of course, I wanted to give some other example, but this is coming to the top of my mind. For example, we recognize people by their faces. Okay, that's a very beautiful thing that we do. When we are exposed to that person for a few days, our cognitive system captures a pattern about the facial distinction or uniqueness of that person. So as a result of that, um, you will be able to recognize that person at a later point of time in terms of recognizing the patterns, rather than you don't do any measurement, physical measurements or pixel values of that face. It's some distinct features you will look into, and that is what is pattern. Okay. Otherwise, if you go by the way computing machines work, where you need data and you crunch data, we never do that. Our cognitive system is more in terms of pattern oriented approach. Even the way you register the route to reach your office from your home, maybe for the first time it may be slightly mentally taxing, but after a few days it becomes a very natural. Even when you're driving on Indian roads, your cognitive activity gets so much tuned that when you are an expert driver, it is descended to the level of your neuronal activity at the nervous system not neuronal activity, nervous system activity to the legs, which can rarely you do mistake of putting your leg onto an accelerator where you are supposed to put onto the brake. Okay, so that way our nervous system gets tuned for that, and that is what is that pattern way of capturing the information. Of course, when I go for the machine learning, that is one way of another glorified way of saying pattern recognition, but there is some distinction where when as the name itself indicates, in a computing machine, we are trying to discover the underlying patterns that are present in the given data points without being explicitly programmed on what is that pattern about, how exactly you should look for the pattern and try to discover that pattern without any explicit of course, there is an algorithm steps to process the data points, and that algorithmic step is independent of what patterns you are trying to discover. That is the why the name of machine learning has come into picture. Machines itself will discover the underlying patterns without being explicitly said what patterns you are looking for. That means to say you have a machine learning algorithm to model the facial information. The same algorithm you should be able to use for modeling the speaker information without explicitly changing anything or using the domain knowledge. And the same way, the same algorithm, you can just move out of this domain and take it to some other digital data that is being generated in some other distinct applications, you can still, there also you want to do a classification task, you can use that algorithm without being explicitly programmed. So by that I mean, when pattern recognition field was there initially, it was more a domain specific and a specialist area. Suppose if I'm working for in the speech processing area for about a decade or two, then I'm becoming a specialist in that area. Now, a novice person wants to come and work in the speech processing. He will always having the lacuna that he does not have the domain knowledge experience for so much long time. But in the machine learning, he tries to make it as domain agnostic. Of course, if you have domain knowledge, it's always an added advantage. But when I go for machine learning, we are trying to move more domain agnostic way, where even if you don't know anything in image processing or video processing or speech processing, you are given data points and also the algorithm, you can still crunch those data points to model information. So to that level, the process has been simplified when it comes to the machine learning. So that is what is meant by this domain agnostic thing. Then coming to the deep learning, where suppose when I go for pattern recognition or machine learning, we are thinking about you are giving the data you are collecting and then trying to extract the relevant features. And then once you have the features, you discover the patterns there. What is done in deep learning is even you don't have to discover the features or process the feature raw data to get the features. You can directly apply to the deep learning model the raw data, and the deep learning model will first discover the relevant features that it can use for further discovery of the patterns. So that is how this deep learning, it will learn the underlying patterns given set of raw data without being explicit. Here, given set of features in the machine learning, in the specialized area of the machine learning, which is we call it as deep learning, where we are trying to learn discover the underlying patterns without from the raw data itself. So that's, you should know the overall, if you see the big picture of artificial intelligence, we have pattern recognition, then we have this machine learning, where you can see the difference between pattern recognition and machine learning. In the machine learning, we are trying to move from domain specific to domain agnostic. When I go to the deep learning, we are further moving away, where I don't have to bother about what feature to extract. Take the raw data and apply to the deep learning model. Okay, so that is how this whole fields are there. Of course, people use these terminologies interchangeably. And even when it comes to the artificial intelligence, there is something called symbolic manipulation, and another is called the connectionist approach. The current generation, when people are talking about artificial intelligence, we are talking about this connectionist approach for artificial intelligence. So this I've already told. I'll go quickly here. So as I mentioned here, intelligence means, as humans, ability to learn and understand, that is that experience, and use that knowledge, that experience for future survival. That is that intelligence means. Okay, that is the human intelligence. So you don't compare that only with the academic performance. He is a rank holder, then he is more intelligent compared to just past student, and nothing like that. This is just the basic cognitive tasks that we employ for survival and interacting with external environment. That is an intelligent activity, and that is where that word of intelligence has been coined. Artificial intelligence means we want to enable computing machines to mimic this activity, where given the raw data, I should be able to learn and understand and use that knowledge for future unseen data handling. That is where this artificial intelligence for mimic discovery, learning, dealing with uncertainties and new situations, and that is where this field of artificial intelligence coming into picture. As I told you, have symbolic manipulation, that is one form of artificial intelligence, still being studied as one course in computer science domain. The other one is connectionist approach is another. Whatever these deep learning models we are telling, they are all driving this artificial intelligence in this decade. Unless specified artificial intelligence, we are looking more from deep learning perspective. This, coming to the pattern recognition, if you recall, some of you, a block diagram of pattern recognition, there are several well-structured modules. Feature extraction plays a very key role, important role to decide on the performance of the system. Okay, that's where there are a lot of emphasis on earlier. There are, if you look into the literature or publications in the pattern recognition arena, 80s, 90s, people were always, a sizable portion of your research contribution or novelty was in terms of features. Some of you may recall when you are doing PhDs early days, people are talking about image processing, discrete cosine transform features, wavelet scheme. These are all essentially feature representations methods. Okay, whole focus was on that, and people were looking down if you don't do a good job on feature extraction. That was the emphasis that was placed on feature extraction at that point of time. Of course, then later comes the modeling. Of course, different modeling strategies were developed. People used to say, okay, first you worry about extracting good features, then you worry about exploring different models to model this information. Okay, so that was, so in that way, so once you develop the model, the modeling approaches are all pattern recognition approaches. Then once you have the models built, how to recognize the patterns. So that was the strategy which was put in the whole pattern recognition block diagram. But I want to draw your attention to these two cases, feature extraction and modeling, which were very distinct knowledge or hard work is required in that area. That is how people were very experts. Speech processing is working for the last 3 decades, means one of the sizable time he or she is spending on what different ways of extracting features from the speech data, speech signal. Similarly, the modeling approach. Okay, there is a modeling proposed by the conventional pattern recognition community without assuming any domain knowledge. Then I take that model and see how I tune this model to suit for my specialization, that is speech processing. For example, Gaussian mixture model. It was proposed as a generic statistical model, stochastic model, then without assuming whether it is being used for speech or image or video processing or natural language processing. But as a specialist in the speech processing area, I first study about the mathematical background behind Gaussian mixture models and see how do I use some of these observations in that mathematical model to suit developing models for the speech case. So with that, that becomes a very specialized domain. People become expertise in that domain, and that is what is the limitation of the pattern recognition field when you look into. Limitation means you need to spend more and more time for feature extraction and tuning the modeling principles to your area. Of course, this whole things were driven by signal processing and probabilistic modeling at that point of time. Of course, they are able to mimic this pattern way of processing by humans on a computing machine. They're able to mimic this and say that, yes, you see, we are able to do pattern recognition on a computing machine. However, the performance of any of these pattern recognition based technologies were much inferior compared to human way of doing pattern recognition. Of course, at that point of time, 70s, 80s, 90s, limited computing power and data compared to what is available now. What it was able to demonstrate was essentially mimic this activity of pattern way of processing the humans. Then came this machine learning. Of course, this machine learning was more from a synthetic digital data, call center data or shopping mall data, where chain of shopping malls are there, lot of digital transaction data getting generated. And this you don't have a luxury like speech signal. I have half an hour data. I will put the waveform spectrogram and do manually analyze to know what sound is there. That type of luxury I don't have. I don't have infinite time to do that manual analysis. I should have just crunch these numbers and see the trends that are happening in the market so that I can take quick decisions on what future changes I have to make. That is where this concept of machine learning was put forward, where I really don't care, there is no domain knowledge there. I have digital data, I have some labels for the digital data, then I crunch those digital data and quickly bring out some trends that are there, unique trends or repetitive trends that are happening. Once I have that, then I can use that knowledge for further human consumption to take a strategic decision. That is what. There, then under that condition, what happens? There is no signal processing, no image processing, nothing there. It is more, in that way, there is no focus on feature extraction there. So signal processing knowledge was not a prerequisite. So that is where it was more like handling digital data. That is where in a mathematical, the closest mathematical way of explaining this, what is happening in machine learning is, if you are given data points, y and x is the input and y is the output, and this is y is that some label, and x is the data points associated with that label. So I am putting all this x to relating to y because there is an implicit relation, functional relation that exists between the input and the output. Now the goal is to learn this implicit functional relationship that exists between the given input-output data points. That is where, and without worrying about it can be regression or classification or clustering or anything, this F can represent anything. So I should have generic methods without feature extract. This X itself, data point itself, we assume it as features. On the other hand, when I go to speech processing, I assume that I don't care what data you are using, the feature extraction you're using, the X features you are giving, which are representing features, the data point itself, I assume it as features. And my goal is to derive the underlying functional relationship that exists between X and Y. So that is where the flexibility came, where that stigma of not knowing signal processing, image processing is no more the requirement if you want to work in even conventional fields like speech processing and image processing. The machine can learn the implicit relation that I. Alternatively, when I come to the deep learning, it was then people were telling, no, you take the raw data, apply it to a deep learning model, and the output layer, you get the required pattern information or class information, how it is happening, how are you feeding the raw data when people ask it. And that is the working principle of the deep learning model. When you have several layers in the deep learning, when you feed the raw data, the first few layers, it will try to decipher the features from the raw data by processing through those nonlinear elements, which are neurons present in the deep learning network. And those are the nonlinear features. And these nonlinear features are further processed to discover the patterns in the later layers. It goes in a hierarchical way. Highest level, you have the class label. Lowest level, you have the raw data. When it goes through the several layers, the raw data gets smoothed layer by layer as moved to the upper layers. And in that way, from the raw data, you get first level of concepts or features. From the features, you get to the next level of gross concepts, which can be, in case of speech, it can be sound units or something. Next, it comes to the next level of information like word or something. So that is how the hierarchy of concepts. So what it says is that is essentially mimicking the human way of processing. When it comes to the human way of processing, what we do is, suppose if you can sit and think over that, whenever you are mastering certain things, on the day one, you will not be able to have the same proficiency as you will achieve that after expertising for some time. So that is to say, at the first day of learning something new, you don't have to be bogged down with all concepts related to that topic or that concept which you want to learn or that area you want to expertise. Initially, you get exposed to some basic things. Once you master that basic things, then you using that basic things, you expand the horizon, you go on. That is how you become an expert after some time. The deep learning models exploit the same thing. From the raw data, It does not jump directly to the class labels. It will process layer by layer to smooth the information and then bring it to the class level. Okay, that is what is the deep learning model, where you apply the raw data and get the class levels. Of course, there is always a question in the mind: what is the difference between a neural network and a deep learning? Structurally, they look same. Okay, one basic distinction we say is, oh, you consider neural networks, it will have only few number of layers. That's where it's called as a shallow neural network. When you go for a deep learning, yes, you have large number of layers. That's why you call it as a deep learning. I understand. So the structurally, that can be one basic difference that may be there between neural networks or shallow neural networks and deep learning models. But the more better reason for coining it as deep learning is because of the hierarchy way of learning the concepts, hierarchical way of learning the concepts. That is what is gives more useful name for this deep learning concept. Of course, here also there are several architectures available. In deep learning also, we have feed-forward architecture like conventional shallow neural network. The same architecture is available. Topology is available. Okay. Of course, this here backpropagation learning algorithm is the workhorse in the conventional feed-forward neural network. But what was observed in earlier arena when neural networks were at its peak, the backpropagation learning algorithm did not work well when you increase the number of layers beyond certain, maybe beyond 2, 3, when you go, it starts saturating performance. Even if you increase, you don't see improvement in the performance. That means to say, there is a limitation in terms of, training or adjusting the weights of all the layers in a good manner. That was the roadblock for using the deep learning networks, which has several layers. Okay. Coming to the breakthrough that happened for the deep learning was Professor Jeffrey Hinton's group in University of Toronto. They felt, okay, if this is the reason for training feed-forward network having several layers, this is the problem we are facing with backpropagation learning, let us change the learning strategy. So what they found out when we go for, when you have a neural network with large number of layers, which we call it as a deep feed-forward neural network, and trying to use backpropagation learning for adjusting the weights of different layers, what was happening was the layers which are there near the output layers, those weights are adjusted properly. But when you move towards input layer, the weights of those hidden layers are not being adjusted properly. And that problem we call well-known problem in deep learning, what is called vanishing or exploding gradient problem. So how to overcome this vanishing or exploding gradient problem? That is what this Hinton group came up with a strategy, what they call greedy layer-wise pre-training. That means to say, each of the hidden layers are trained separately, so that the parameters or the weights of that hidden layer are better exposed to the input and the expected output of that hidden layer. Once that is what is called as a pre-training. Layer-wise, you do pre-training. Once you do that pre-training, then you stack all the hidden layers together to form that big network. Then you try to use backpropagation just to connect all of them together for few iterations. You don't require large number of iterations. Of course, still we are not overcome the problem of the backpropagation in terms of whether it will improve the backpropagation. It will not improve, but what happened is where we were unable to reach the input layers and adjust the weights properly, now we are able to do a better job because of the pre-training. So that was the advantage of this one. And they showed that they have come up with wonderful results which they were unable to see earlier. Of course, when they put forward this idea, they demonstrated on deep belief networks. Of course, many other groups working in the deep learning, they tried to independently reproduce the results on different deep learning models. All of them are able to reproduce the results based on this greedy layer-wise training. Thus, it became, it caught the attention of the community, and rest is history. Okay, after that, no, people moved out and no, started working in the different day. Now, coming to the that is about the know how the breakthrough happened in the deep learning. Now, let us see all these development that have taken place, starting from the journey of pattern recognition to deep learning, and the breakthrough happened in the deep learning. Now, we will see how people have done in these three generations: pattern recognition generation, machine learning generation, and deep learning generation. Coming to the first speech processing using pattern recognition approaches, uh, the starting point is whatever information you want to model is assumed to be a pattern. Okay, that is the starting point, and that is remains same for pattern recognition also, machine learning also, deep learning also. But as I mentioned earlier, feature extraction is an important step done by the signal processing for the speech processing area. That is how we had many speech signal processing methods that were uniquely developed for speech processing, starting from digital signal processing. Like we have linear prediction analysis of speech. I see one session to be handled by Professor Uday Shankara in that direction. So linear prediction analysis of speech is one well-known speech processing technique, which is an application of signal processing. We have Kepstral analysis, which is another important feature extraction method. We have what is called sinusoidal analysis. There are many feature extraction methods. There are a lot of emphasis on developing a new feature extraction method for the speech signal processing. That is one of the vibrant research field as a part of the pattern recognition direction. Then any automatic speech recognition, speech processing task is assumed to be a pattern recognition task. When you say pattern recognition task, you have feature extraction, then you model the pattern. Okay, and you should a priori say what is that pattern you want to discover. Okay, oh, this face is a pattern, or sounds are the patterns, basic sounds of the language are the patterns I want to recognize. I want to recognize the gender present in the speech signal. That is the pattern I want to recognize. So a priori you have to say what is that pattern to be discovered, and signal processing, feature extraction, what you are doing. So with all that thing, what was important was the domain knowledge became a must when we want to develop pattern recognition approaches for speech processing. And the approaches are for explicit modeling of the pattern. So a priori, you know what pattern you're looking for, and how do I use that pattern knowledge, whatever the a priori knowledge about the pattern, in tuning my algorithm for better modeling the pattern information. For example, if the pattern lies in the time series data, then I better use hidden Markov models. If the pattern lies in only spatial distribution of the data point, better use the Gaussian mixture model. Like that, people were using a lot of expert domain knowledge for deciding on the modeling also. Of course, the same clustering, Gaussian mixture model, hidden Markov model, neural networks, supported vector machines, people use it for pattern recognition tasks. Now comes the next thing. What happened was, in terms of speech processing, is machine learning. Here, the basic distinction is, even though we call it as a pattern, but the machine learning community call it as the information to be modeled is assumed to be a function that is present between the given input and given data point, present in the given data points. Okay, and as I mentioned, feature extraction is not a major task. An automatic speech processing task is assumed to be a machine learning task now. Domain knowledge is not very important here. So you don't have to be a signal processing expert to extract the relevant features. So we assume that it's a black box. You feed the speech data, it generates relevant features. That features, as a computer science engineer, I just treat them as data points. Go ahead and discover the function, implicit function that is present among the data points. So domain knowledge is not important, and approaches for implicit modeling of the pattern as a function. That is there it was explicit modeling of pattern. It is an implicit modeling of pattern as a function. So if you see here also, most of the modeling techniques that we were using in the pattern recognition, same modeling techniques we also use it. Gaussian mixture model, hidden Markov models, neural networks are same thing. Then how does the machine learning and pattern recognition differ? That is why some of the researchers say these are the two faces of the same coin, pattern recognition and machine learning. But if you ask me if there is any distinction, yes, the distinction is in terms of how do we view, whether view from this side or that side. When I view from machine learning side, I don't care about the feature extraction. When I view from the pattern recognition, I give a lot of emphasis on the feature extraction. Similarly, when I view from pattern recognition, I treat everything as a pattern, domain knowledge. But when I go for machine learning, I view everything as an implicit function to be learned. That is the final distinctions, if you want to call, between pattern recognition and machine learning. Otherwise, we can use them interchangeably. Coming to the deep learning approaches, once the breakthrough came in 2006, first people demonstrated the advantages of deep feed-forward neural network in 2012 for acoustic modeling task in the speech processing, which I'll explain in the later slides. And many more things came: deep belief network, deep autoencoders, generative adversarial networks, convolutional networks, time delay neural networks, recurrent neural network, long short-term memory transfer, so many things. So you can just go on naming. Many deep learning models come now and then nowadays. Of course, you can broadly group these all deep learning networks into unsupervised way of learning, supervised way of learning, and hybrid learning. People also talk about other types of learning like reinforcement learning, federated learning, all those things. Even though there are n number of models.
Excuse me, sir.
Yes, madam.
Hello.
Yes, please.
Sorry to interrupt, sir. I have one question to ask, sir.
Yeah,
So
please.
my research domain is also NLP, and I'm doing POS tagging using deep neural network. Okay, sir. I trained my data set, Kannada data set in deep learning with LSTM layer. I didn't understand what are feature extraction in that and what are the weights that we are going to assign during training. I assume that the weights that we are assigning is POS tags, and the feature extraction in the POS tagging, I didn't understand in that
The
area.
See, the feature extraction I am not from the NLP domain. I am the
Okay, sir.
task we work only in the speech processing, which is quite distinct. However, no, my guess is, see, whatever the labels you prepare, pre-processing you do for the text part, and give it as input variables to your deep learning model, those are treated as the features. Okay, and
Okay, sir.
then you the information that you are trying to model, they will be taken as the weights of the network. Sorry, I don't have a better answer than this. Okay, since I don't.
Okay. Thank you, sir. Thank you, sir.
So just quickly to give some examples, suppose we have deep neural networks for acoustic modeling. Acoustic modeling means given speech signal, decode the sequence of sounds that are present in the signal. That's a well known. This Professor Hinton and many other parallel groups from worked on this, and they published this paper, Deep Neural Networks for Acoustic Modeling in Speech Recognition, the shared views of 4 research groups, which is Signal Processing Magazine 2012 result. What they wanted to show is, since this is one of the important tasks in speech processing area, how a deep learning model provides performance as opposed to the earlier models like machine learning or pattern recognition model. A greedy layer-wise training they did. So I will, no, you can read that. I'll just, what is important is, for example, the Gaussian mixture model, HMM model, can be treated as a pattern recognition machine learning model. It was giving a phoneme error rate of 27.3%, whereas initial deep learning neural network gave about 23.4%, which is an improvement, significant improvement over the earlier GMM HMM model. Okay. Why it is called a significant improvement? Because when we work on this acoustic modeling, the performance should be as low as possible. Ideally, it should be 0. But people were stuck in hovering around this 27% for a very long time. Somebody produces a new paper with some 0.5% improvement and go for some different data conditions. Again, it falls back to 27.3 only. So for a nearly decade or two, we are stuck in that point. It's like a local minima. We are unable to get out of that local minima. This gave a flip where quickly an absolute improvement over 4% really caught the attention of the community. Then they modified this basic deep neural network in terms of other variants like deep belief network and convolutional deep neural networks, which gave further improved the performance from the initial version by pattern recognition machine learning models. So that is what is being reported here in 2012 paper. That is the next story, which shows that using deep learning approaches, we can improve the performance of the speech systems or speech technologies in a big way. This is about the acoustic modeling. Then acoustic modeling happens as an important module for automatic speech recognition. When I go for automatic speech recognition, they were also able to bring from 23.3% to about 16%, which is a very, very big jump in the performance, which is a step change in the speech recognition performance. Similarly, another data set from 27.4 to 18.5, which is another big improvement in the performance. So that is how it captured the attention of the community. Initially, it is demonstrated for speech recognition, which is an absolute 10% improvement in the performance. People used to call it as a next breakthrough that has happened in the speech processing area. So these were the reasons. Of course, now it would have gone much lower than this. When I take all these commercially available technologies, they exploit these deep learning models for acoustic modeling as well as the latest language modeling and speech recognition. Then the other areas, sub areas in the speech processing took the developments in the deep learning seriously. So accordingly, the next task was speaker or language recognition. Here, as the task indicates, it's only recognizing the speakers, not the message part. Initially, in the PRML approach, we had clustering, dynamic time warping, Gaussian mixture model, hidden Markov models, and the latest there was I vectors, identity vectors. Then the journey started in the deep learning things. People started using deep autoencoders. Then they used X vectors, which are based more on. So if you see, if you take some data sets, again, equal error rate is a parameter, performance parameter, which is ideally it should be 0. And I vector thing, which is a non-deep learning approach, it was giving about 7.45% result. Then here the features were from a conventional signal processing method. In place of that, they extracted the features using the neural networks, which is called as bottleneck features, using a deep autoencoder. It improved the performance. In place of that, instead of doing this I vector extraction from the bottleneck feature, the vectors itself, they are extracted directly from the deep learning network. They are called as X vectors. You can see that also gave a significant improvement in the performance, absolute improvement. Of course, you may say whether 3% improvement is a big improvement. Yes, it is so when you are reaching this single digit performance. When you are having 7%, going to 4% is a harder task. Same way they evaluated on different data sets also. From 9.23 it came to 5.7. So in that way, here also it was proven that when you go for deep learning models, then you achieve significant improvement. But there is one point which I am not emphasizing here. I am assuming it is a fact that these improvements are when you have large amount of data available. If you don't have enough data, then you may not see that benefit coming from the deep learning model. Same way, in the spoken language recognition task, where you're recognizing the spoken language, here also performance improvement was seen as you go from I vector bottleneck features to deep learning model like LSTM from 11.8 to 8.35% it came. Same thing for generation of speech by machine. Nowadays, the speech synthesis quality, generated speech from the computers are so high, it looks almost like a human speaking the other way, on the other side. Just like I mentioned when I was talking to the robot yesterday, voice robot, it was almost like a person speaking. That type of, even people are now confused whether it is a synthetic speech or it's a human generated speech. That itself, there is people have taken as a research area and given a speech segment, whether you find out whether it is human generated or machine generated speech. That type of quality has been achieved. Earlier, we had a hidden Markov model based synthesis. The quality was opined on a 5-point scale about 2.86. 2.86 was not very great in terms of human acceptance. Initial attempts for employing the deep belief network, it came to 3.09. But the later thing, many results came. WaveNet is one deep neural network which gives about, on a 5-point scale, about 4.2, and whereas the natural speech from human generated about 4.46, which is nearing the human level performance. So that is where the advantage of this deep learning network comes into picture. Okay, so these were some of the case studies to mention that deep learning indeed, without doubt, provides significant improvement in the performance. Of course, there are other strategies, like now recently we talk about end-to-end strategies. If you want to do multiple, one concept to the other concept learning, for example, speech-to-speech translation. If I know two languages, spoken languages, I can listen to the speech produced in one language, source language, and my cognitive system can convert that into speech in the target language and produce the speech. So when we want to mimic this activity, speech-to-speech translation on a computing machine, what people thought about is, okay, you take speech signal, you listen to the speech signal, and first what you do is convert the speech into text in that language, then use natural language processing from text in the source language to the text in the target language. Then from the text in the target language, you generate the speech in the target language. Of course, it is fine as a computing mimicking approach, it is fine. But as humans, we never do this intermediate language, natural language processing. We directly translate from speech in the source language to the speech in the target language. And that is what is this end-to-end strategy. Given input is speech in the source language, output is speech in the target language. Okay, so that is what is the level people are looking into the trends and understanding the speech perception, how exactly we perceive different information source in the speech signal. Then how do we find out? So as humans, we are our cognitive systems are well tuned for appreciating the quality in the speech signal. Anything which is poor quality, we will not be able to use it or getting exposed to it for a long time. And also how to estimate the non-verbal cues. Okay, from the non-verbal cues, how do you make out the message part of it, what is being conveyed? And also the cognitive speech processing aspect, all the cognitive activities, not only for speech mode, but other cognitive activities also can we decode in this area of cognitive speech processing. So these are the tasks people are looking into. Summarize about the modeling higher level information. Now people are dreaming about building speech systems which are really trying to mimic the cognitive activities other than whatever the conventional activities that we are looking for. Summarize, so we have made a significant progress in adding values to the computing machine, starting earlier approaches of pattern recognition to the latest deep learning to handle these intelligent tasks. Of course, we have also added to the literature development in the field like signal processing, stochastic modeling, pattern recognition, machine learning, and now deep learning. The performance of the deep learning based speech technologies seem to be very good, comparable to human level performance. As a result, we have deployed them in the practical scenarios. So that created a lot of interest in the speech processing area. So as I put out some results from the literature, the latest trend is giving significant improvement in the performance, which can be attributed to the speech processing, which in turn can be attributed to the GPU and the other way of collecting with less difficulty collecting large amount of digital data. Then, as I mentioned, we feel the next thing which we may have to consider, along with continued improvement in the performance of the traditional speech technologies, it is the time to think over how do I model other level of higher level information that I presented in the previous slide. Many of you can, for example, selective attention is one important cognitive speech processing task. How do we provide that cognitive selective attention from the speech signal? Because practically we mimic using multiple microphones or multiple sensors and try to use that knowledge to locate the source and all those things. But as a cognitive system, it has only 2 ears. With the help of the 2 ears and the cognitive system, which is able to localize the sources. How do I do such cognitive speech processing tasks? So that can be the research direction what people are thinking about. I think there is this more exciting, and also there is a lot of fusion happening between speech processing and natural language processing as a result of this. I think we may have to know, if you are interested. I think there are good sources available in the public domain, both in terms of toolkits. Codes are available in the public domain nowadays, so you can make use of that. Now there are several openly available data sets, speech databases, which you can exploit for building technologies. So in that way, it's an exciting period of time in the speech processing area to build technologies in a quick time, which you will enjoy in terms of the performance it is giving. So with these statements, I will conclude my talk. I'll be very happy to take some questions now. Thank you very much for listening.
Participants, if you have any questions, you can raise it for sir. 1 or 2 questions.
Hello, sir.
Yes, please.
Could you please highlight feature extraction and the weights assigned, at least with respect to speech analysis in the speech recognition?
Mm.
What are weights there in the speech, and what are the features?
See, when we are doing deep learning, before this deep learning came into picture, one of the well-known features that we were using was capsular analysis. In that, specifically Mel frequency capsular coefficients. Okay, this was some of the default features people were using for a long time. Even the initial first attempts of deep learning approach also, they used a Mel frequency capsular coefficient. If you go to the 2012 paper and look into that, but later they felt that you don't have to use that type of Mel frequency capsular coefficient. You can go one level down. Before Mel, if you look into the Mel frequency capsular coefficient, it is nothing but the discrete cosine of the filter bank energies. You can directly take the filter bank energies themselves as the feature representations for the speech process. So that is how one of the mostly used approaches nowadays is filter bank energies. Of course, people are still working on how to avoid this filter bank energies also. Just a simple way of smoothing that can happen onto the speech signal, those can be used as features for any of the speech processing tasks. So that has been the latest feature things about that. Weights means essentially, suppose if I want to give a rough guess, if I use filter bank energies as input to the deep learning network, first 2-3 layers, we can 1 or 2 layers, depending on number of layers you have put, 1 or 2 layers may be considered as nonlinear way of extracting the discrete cosine transform. Okay, so that is what happens, and the weight parameters are essentially adjusted, where if you see the output of the neurons in the first layer, hidden layer or something, they are tuned more towards combining these filter bank energies and computing the DCT as the output, but processed in a nonlinear manner. That is how these weights are there. Suppose when you go to the first or 2 layers, maybe it is combining like that. After that, these weights, further layer weights, are in terms of tuning towards a specific sound. For a particular sound, sa, how the weights gets tuned. That is what is being captured in the later layers. That is how, whatever, suppose you take a pattern recognition task or a machine learning task, the output layer will have the pattern to be learned, and this pattern can be expressed in terms of hierarchy of concepts. And the lowest level concepts will be modeled by the parameters or weights in the first hidden layer. Similarly, the next layer level of concepts can be modeled in terms of the second hidden layer weights. That is how it will happen. Hope I have answered the question.
Thank you for enhancing my speech field, sir.
Thank you very much.
Next, Shubha. Sir, can I know that one more thing that in modeling using deep neural networks.
Mm.
So you told us many breakthroughs that has attracted the research people in making a choice of either PR or ML or DL. So according to the state of art, sir, so what is the breakthrough that we could identify and work towards research in terms of DL, and how much error rate it has got reduced
Mm. So,
compared to PR method, sir?
yes,
PR or DL sorry, PR or ML method,
yes.
because nowadays deep learning is taking the field.
Yeah. So without exception, no, the modeling techniques we may have to strategize is only using deep learning models. Whatever the see now, what happens is, since this deep learning has caught many fields, we can look into the simultaneously other areas. For example, computer vision, image processing, video processing, or even natural language processing. How the latest deep learning models they are developing there and producing significant improvement over the earlier deep learning models that are there. So based on that, we get an idea. So once you do that we can bring the deep learning model and see conceptually whether it suits our pattern recognition task that we are trying to do in the speech processing. So in that way, for example, transducers is known to be a recent breakthrough in terms of natural language processing. Then how do I bring that back into speech processing and working on that? That is how people are looking, uh, wherever the deep learning architecture is proposed, that is being brought to the speech processing field and see how it can be employed here and try to um, improve the performance.
Okay, sir. Sir, in the area of speech signal processing, so how far the deep neural networks has played its major role in increasing recognition accuracy, sir?
Yeah, can you repeat the question?
Using the deep learning model applied to the speech recognition application compared to GMM models or HMM models, what is the performance increment that we could find in terms of recognition accuracies?
Correct. So that have shown in some of the previous slides,
Slides, okay.
where it has shown absolutely about 10% improvement in the performance, absolute 10%, which is, suppose if I are in a layman term, if I want to say the performance is almost equivalent to that of human level performance. Even humans, if you do the speech recognition on different environments, they may not give 0% error.
Error.
They also give some 4-5% error. Same thing is we are able to achieve in the existing speech recognition systems using deep learning.
So that we are nearing about 98%, sir, using
Yes,
deep neural.
yes.
Sir, please suggest us for stuttered speech recognition any databases we could use other than UC class, sir. If you are, if you can throw some light on it.
Oh, I have no idea about this pathological speech processing, because the stuttered speech, that the University of this one, no, Urbana Champaign, that is the only data I see in the public domain.
Okay,
Because
sir.
I'm not working in the field, I do not know really.
Fine. Fine, sir. Fine, sir. Thank you, sir.
Hello,
Sir?
Yeah,
Hello.
please.
sir.
Yeah.
Sir,
Sir,
which is the best platform for speech processing? Python or MATLAB?
Harman, what you so see, if you see, if you want to make use of latest open source codes that are available in the public domain, Python is the way to go about. Many deep learning routines are written in Python. So accordingly, it is better to use Python.
Okay, sir.
sir, hello, sir.
Yeah, please.
Sir, are these dense layers same as hidden layers? Are both layers and hidden?
See, see what happened was earlier when shallow neural networks were
Hello.
there, connections are all dense.
Yeah.
Every neuron in the previous neuron gets connected. Earlier, when they were using this neural networks, every layer was a dense network because every neuron in the previous layer gets connected to every neuron in the next layer. Okay, but that is in the deep learning architecture scheme. No, some of them, no, they need not be that condition. We avoided this dense connection. Okay, but it does not matter. The layers which lie between the input and output layers are termed as hidden layers. Either these hidden layers can be either dense or no, the opposite word of the dense. I don't have a quick term coming to mind.
Okay. Sir, and this is the role of optimizer in dense, sorry, in neural network, sir, deep network, optimizer.
No idea. Maybe to optimize your this one
Or to
objective.
reduce the error rate.
Yes, reduce the error rate. That is one way of optimizing the network parameters. Maybe that's the way they are thinking.
Okay. Okay, sir. Thanks, sir.
Thank you.
Hope all the questions are over from the side of the participants. So, on behalf of the college and the department, we thank you, sir, for sharing your vast knowledge with us and our participants. And you throw light on many areas, that too majorly with the breakthroughs in the literature, which was very catchy from the researchers and which made them to work ahead. And also you told many informations regarding the modeling of different mathematical models with respect to PR, pattern recognition, machine learning, and the deep learning. So, and also you told us about modeling the higher level information. The talk was very informative, sir, and it made many research to think in different directions, and hope that would be useful for them. We are thankful to you, sir, for accepting our invitation and delivering your talk in this session. Thank you very much, sir.
Thank you very much, madam. Thank you for this opportunity. Hope some points will be useful to some of you and excite all of you to work in speech processing area.
Definitely, sir. If things are there, we'll feel free to contact you and get the information from you, sir.
Thank you very much. I have sent these slides to you, madam.
Yes, sir. Yes, sir. It will be shared for the participants.
All the best
Yes,
for FTP. Thank you very much.
yes, sir. Thank you so much, sir. Thank you.